Section 12.3. So before we talk about inscribed angles, let's remember about another kind of angle. So let me draw my circle, and here is the center, and I'm going to draw this. What did we call that kind of angle in a circle, where the vertex was at the center? It's a central angle. So this is a central angle. Our vertex is at the center. And do we remember how the degree measure of the central angle and the degree measure of the arc were related? They're the same. So the angle and the arc are the same. So the measure of the angle, and I'll call this AB, measure of arc AB equals measure of the angle. So for central angle, the arc and the angle are the same. We're going to talk about a different kind of angle today. We're going to call it an inscribed angle. So this is a central angle. So for a central angle, the arc and the angle are the same. An inscribed angle is an angle with its vertex on the circle. So here's our picture of a central angle, or an inscribed angle, sorry. So there's my circle, and the inscribed angle is going to have its vertex on the circle, like so. There's my vertex. So there's my vertex. And I'm going to call this angle ABC. So this is an inscribed angle. And what we're interested in today is how the angle and the arc measure are related for an inscribed angle. So this is our first theorem, our inscribed angle theorem, tells us, anybody want to guess? The measure of an inscribed angle is, anybody want to guess how the measure the angle and the measure the arc are related? Good guess. Half. Is half the measure of what we call arc AC is the intercepted arc. So if I'm going to highlight this in red, arc AC is the intercepted arc. We have the inscribed angle and the intercepted arc. And if we write this in symbols, we can say that the measure of angle ABC equals half the measure of arc AC. Or we could turn it around and say the measure of arc AC equals 2 times the measure of angle ABC. And the way I draw it on my pictures is to go from the arc to the angle, multiply by 2. From the angle to the arc, and from the arc to the angle, we divide by 2. And we could also write this, we could say the angle, just in shorthand, equals the arc divided by 2, or the arc equals 2 times the angle. Just to give it a little shorthand. So that's how our inscribed angle and the intercepted arc are related. And we would show this by drawing in the center of our circle, drawing in 2 radii, or maybe splitting this in half along the diameter, and showing that triangles are congruent. So we'd make this into triangles, so the triangles are congruent, and from the triangles we could figure out how the angles are related. So we turn this problem involving a circle and one angle into a problem involving triangles, and then we can show that what we're saying about the angles and the arcs is how it works. All right, questions on our inscribed angle, what it is, and how it's related to the intercepted arc. All right, so let's look at an example, and then all we're going to talk about for the rest of the lesson is just some other things that we can figure out because we know this is true. We call them corollaries. Some other little theorems that we can figure out from this. All right, so a couple of examples. Here's my circle, and I'm going to draw in some segments here. We end up with lots of pictures that look like this when we're dealing with circles. And I'm going to say this is 56 degrees. That arc is 56 degrees. This angle is 52 degrees. And this is going to be B degrees, and this is going to be A degrees. And we want to find A and B. All right, so what I recommend with circles, if you have them, use highlighters or colored pencils. So I'm going to highlight the first thing that jumps out to me about this problem is I have an intercepted arc here, and it is related to this inscribed angle. So I have the inscribed angle and I have its intercepted arc. So we can figure out B really easily here. So how do we go from the arc to the angle? Divide by 2. So B equals 56 divided by 2. So I get 28 degrees. And now I'm going to highlight in a different color. I'm going to highlight another inscribed angle that we know something about. There's the other inscribed angle. And here is its intercepted arc. All the way around there. So from this, what arc can we figure out the measure of with this information? We can figure out the measure of arc AC. The measure of AC, how do we go from the angle to the arc? Double times 2. So the measure of arc AC equals 52 times 2, or 104 degrees. So the blue arc is 104 degrees, the red arc is 56 degrees, so how do we figure out what's left for A? Subtract 56 from 104. So A is 104 minus 56, and I get 48 degrees. So we could use those two pieces of information. We had to do just a little bit of work, multiplying by 2 and dividing by 2, and we were set. Questions on that example? These problems are kind of like our triangle problems, where we figured out the angles, and parallel lines where we figured out our angles and figure out all the missing pieces. Kind of the same thing. Kind of like Miss Lindgren said, like a puzzle. All right, let's talk about our corollaries. And we've talked about corollaries before. Corollaries just mean other theorems that we can figure out very easily from our main theorem. So our main theorem is for an inscribed angle to go from the arc to the angle, divide by 2, to go from the angle to the arc, multiply by 2. So corollaries to that. Extra little things that we can figure out very easily. Inscribed angles that intercept the same arc are congruent. So if we have a picture here, our picture for this corollary is, here's my circle, and we'll draw in. We'll see a lot of drawings that look like this for our circles. And I'm going to call this angle A and this angle B. And here's my intercepted arc. Both those angles intercept the same arc, so angle A is congruent to angle B. So that's a nice one, a nice little thing that we can figure out right away, because we use the same rule to get to angle B as to angle A. Divide the arc by 2, and we get to both of those angles. All right, questions on that corollary? That one sounds pretty easy. All right, let's look at the next one. Another really easy one. Next one tells us, our second corollary, an angle inscribed in a semicircle is a right angle. So let's draw our picture. First off, what's a semicircle again? Half a circle. Semicircle is half a circle. So I have a chord that goes through. When I have a dot there, the dot's the center of the circle. So if we inscribe an angle in the semicircle, there's our inscribed angle. And it says this is a 90-degree angle. And this one is really easy as well, because how many degrees is it halfway around the circle? 180. To go from the arc to the angle, we divide by 2. 180 divided by 2 is 90. So that one's a really easy one to come up with. And it doesn't matter where we put that intercepted arc. Or the inscribed angle, I could put it here, I could put it way over here. Those angles are always 90 degrees. And then our last corollary has to do with quadrilaterals. The opposite angles of a quadrilateral inscribed in a circle are supplementary. Now let's remember, what does supplementary mean? Add to 180. So our picture here, draw a circle, and we're going to inscribe any quadrilateral. Doesn't have to be any specific kind of shape, as long as it has how many sides for a quadrilateral? It has to have 4 sides. So there's a quadrilateral, and I'm going to say that's A, B, C, and D. And what this corollaries tells us is that the measure of angle A plus the measure of angle C is 180 degrees, and the measure of angle B plus the measure of angle D equals 180 degrees. And this comes from the fact that from all the way around the circle is 360 degrees, and the opposite angles are getting opposite pieces of that 360 degrees. That's how they end up adding to 180. So we turn this into, again, into a problem involving triangles, and we can figure out the measures of our angles and figure out that they add up to 180 degrees. So anytime we have a quadrilateral inscribed in a circle, the opposite angles are supplementary. All right, questions on that corollary? Nothing too complicated today, so that's kind of nice. All right, so what I'm going to do is look at a couple of examples using these corollaries, and then there's one other theorem we need to talk about that's really not different than what we've talked about. It's just a slight little thing that we have to pay attention to. So a couple of examples. Let's do an easy one first. This one should be really easy. All right, so what have I drawn there on my circle? I've drawn a diameter. So I have a chord that goes through the center, have a diameter. What's the measure of angle 1? Hmm? 90. This is a diameter. This is a semicircle. This is an angle inscribed in the semicircle. So measure of angle 1 is 90. It's inscribed in a semicircle. So that one's really easy. Let's look at another one. Little more work involved in this one. Still not too bad. Here's my picture. And I'm going to call this point C, B, A. We're going to say that's 43 degrees. That's angle 2. And that's 128 degrees. And we want to find measure of angle 2. But what's measure of angle 2? Is it 43? Let's do a little highlighting here. Here's one angle that we know, an inscribed angle that we know. Here's another inscribed angle that we know, or that we're looking at. What do these two share? They share arc AB. So they both intercept arc AB. Two inscribed angles that intercept the same arc are congruent. That was our first corollary. And if we didn't remember that corollary, we could figure it out. To go from this angle to the arc, what do we do? Go from the angle to the arc. Double it, times 2. So the arc is going to be 86 degrees. To go from the arc to the angle, we divide by 2. 86 divided by 2 is 43 degrees. So we can figure it out either way. So we could remember a corollary, that because these intercept the same arc, they're congruent, or we could figure out the measure of the arc, and then figure out the measure of the angle from that. We could do it either way. Questions there? All right, so questions like this, figuring out these kinds of things, that's the kind of thing that's going to be on the quiz. All right, let's look at our last theorem. This one doesn't have a special name. Theorem. And for this theorem, we're going to say an angle formed by a tangent and a chord measures half its intercepted arc. So let's draw a picture of this. This sounds different than what we were talking about before. It really isn't. So a chord. Here's my chord. And here's my tangent. Let me get a tangent. Let me go. Let me get it right in between there. There we go. And this is going to be tangent AB. And we'll call this C and D. And what we're saying is that line AB is tangent to the circle at C. And we're going to say that the measure of angle DCB is 1/2 the measure of arc DC. Or we can say it the other way around, that the measure of arc DC is 2 times the measure of angle DCB. So our angle here, our angle is angle DCB, and the intercepted arc is the arc all the way from the end of the angle all the way around to the tangent point. This is the exact same rule that we were talking about before. The vertex is on the circle. So our rule is exactly the same. So anytime our vertex is on the circle, our rule is the same. To go from the angle to the arc, we multiply by 2. To go from the arc to the angle, we divide by 2. And it's the same rules that we talked about before. We can say the angle equals the arc divided by 2, or the arc equals 2 times the angle. Exact same rules, because our vertex is on the circle. Doesn't matter if we have a tangent or another chord. As long as our vertex is on the circle, our rules are the same. Now, one place that students get tripped up here is a lot of times they'll see this tangent and they'll say, oh, that angle there, because that's a tangent, is 90 degrees. Why is that angle not 90 degrees? Or when would that angle be 90 degrees? If our chord was a diameter. So if the tangent is tangent to a diameter or to a radius, then the angle is 90 degrees. But otherwise, we have to use this rule. So the only time we get a 90-degree angle there is if we're tangent to a chord or to a diameter or to a radius. Otherwise, we have to use this. And this rule would still work to figure out, to measure that angle if we were tangent at a diameter or a radius. Because if we were tangent to a diameter, what would this arc be? Let me draw a picture. If we had a diameter like so, this is a diameter, and here's my tangent. What's this arc? How big is this arc? How many degrees? 180. To go from the arc to the angle, divide by 2. So that makes that a 90-degree angle. So the rule works no matter what. The same rule will work no matter what. So, but the only time we get a 90-degree angle is if we're tangent to a diameter or to a radius. All right. So I want to talk about that because a lot of times we think of these things as all separate rules. They're all connected. It's the same rule. All right, last example. Let's look at an example using this idea. So here's my picture. There we go. And we're going to say that line AB is tangent to the circle at, I'm going to call this point E, at C. The measure of angle, or the measure of arc, CED, is 214 degrees. We want to find the measure of angle DCB. All right, so here's an example of a lot of times where students would say, oh, well, that's tangent to the circle, so that has to be a 90-degree angle. This isn't a diameter, so we can't use that idea. So let's highlight some things. Here's the angle that we're interested in. So in order to figure out that angle, we need to figure out the measure of this intercepted arc. That's the red there is our intercepted arc. But the problem tells us that this green arc is 214 degrees. So what are we going to do? All the way around the circle is 360 degrees. We know this part is 214. So to figure out what's left for this part, we subtract the measure of arc DC is 360 minus 214, and we get 146 degrees. So this arc is 146 degrees. To go from the arc to the angle, we do what? Divide by 2. So the measure of angle DCB is 146 divided by 2, and we get 73 degrees. So a couple of steps and we have our answer. All right, questions? So big picture today, inscribed angle when our vertex is on the circle, to go from the angle to the arc, multiply by 2, to go from the arc to the angle, divide by 2. That's our big idea for today. All right, homework. All right, there we go. Let me